Today we are walking through the paper titled Natural Language Agent Harnesses.
Can we start with the big picture of what this paper is about?
This paper argues that harness engineering is now a major source of agent performance, but the actual control logic is usually buried inside controller code and runtime conventions. The authors ask whether the high-level logic can become a portable executable artifact that we can read, compare, migrate, and ablate.
What exactly is broken in the usual way people build agent harnesses?
The main problem is that harness logic is hard to transfer, hard to compare, and hard to study as a scientific object when it is mixed together with back-end details. The paper also says prompt-level context engineering is too narrow, because real harnesses manage tools, verification, multi-step structure, and durable state, not just one model call. The object they introduce for that job is the Natural Language Agent Harness, or NLA.
What exactly goes into an NLAH?
An NLAH is not just a prompt template. It makes the contract, the roles, the stage structure, the deterministic adapters, the state rules, and the failure modes explicit, so the harness becomes readable and executable rather than hidden in controller code. Now let us put the main system diagram on screen.
In this design, where is the key split?
The split is between shared runtime semantics and task family harness logic. The harness carries the roles, contracts, adapters, and state conventions for a family of tasks, while the intelligent harness runtime keeps the in-loop language model, the two-line child agent backend, and the runtime charter that defines how contracts and state are interpreted. A second diagram shows how the paper instantiates that split in the experiments.
Why is that mapping important for the evaluation?
Because it lets the authors change harness logic without quietly changing the whole infrastructure. In their setup, Codex is the backend. The runtime charter is packaged as a runtime skill, and benchmark-specific policy becomes a harness skill. That makes module ablations and code-to-text migration much easier to interpret. The paper also formalizes what a task handed to the runtime contains.
What should I read in that equation first?
Read kappa first. The task is the prompt B, the input files are linked resources F sub n, and an execution contract kappa. That contract names the required outputs, the budget, the permission scope, the completion conditions, and the output pass, so the runtime knows what success is supposed to mean. Then the paper defines an agent call, which is the runtime step that executes under that contract.
How is that different from an ordinary single model call?
It returns more than text. The runtime step produces designated artifacts say sub t, environment changes delta omega sub t, and a final normalized response y sub t. That is the paper's core shift from one-shot completion to bounded agent execution with explicit state change and explicit success gates.
How do they test whether this harness UX actually helps?
They evaluate onto benchmark families with shared runtime assumptions. SWE Bench Verified measures repository issue resolution. OS World measures desktop task success. And the paper studies 3 questions. How the runtime changes behavior, which harness modules help when composed or ablated, and what changes when native code harnesses are migrated into natural language. Now let us switch to the module ablation result on SWE.
What pattern should I look at first in this chart?
Start with the left panel. Self-evolution is the only module that moves clearly upward without moving far to the right, reaching about 80% solved rate, while staying near the low-cost region. Verifier and especially multi-candidate search are dominated here, and dynamic orchestration stays close to the basic baseline and score.
And what does the right panel add beyond that cost view?
It shows why the authors do not judge modules only by standalone accuracy. File back state in self-evolution, lift the union solve set with basic to roughly 84 to 85%. And even modules that look weak alone can still recover extra boundary cases when paired with the basic harness. So the interesting effects sit on the solved frontier, not in a uniform shift of every task. The table-level results make the benchmark differences clearer.
So which modules help where?
On SWE, self-evolution is the biggest standalone gain at plus for 0.8 points over the 75 point to basic baseline. On OS World, file back state is best at plus 5.5 points, while self-evolution and dynamic orchestration each add to 0.7. Verifier hurts OS World badly in this setting, which is a useful reminder that these harness modules are not universally good.
What does the code-to-text migration study actually show?
The migration story is concrete. The native side exposes 36 main traces plus 7 short nested search branches, while the migrated side keeps third eye for retained inner event streams and to missing inner stream stubs. Search still works, but it moves into the runtime flow, and verification shifts from screen plausibility toward path-addressable evidence such as files, reopened documents, package objects, and system queries.
What should I keep as the final takeaway, including the risk side?
My takeaway is that the paper is not trying to replace code with prose. It wants the high-level harness logic to become readable, portable, and experimentally comparable, while deterministic code still handles tools, adapters, and sandbox enforcement. The authors also warn that portability can spread risky workflows more easily, so provenance, review, permission control, and sandboxing remain part of the design.
So the win is making harness design inspectable and testable, then measuring which modules actually help on coding and computer use tasks.
That wraps up this paper walkthrough.